Hey guys, welcome back. So what we're looking at today is 3.9, my irrational and imaginary friends. So yes, there is such a thing as an imaginary number. No, it doesn't mean you just get to pick whatever number you want it to be because it's imaginary. It's an actual mathematical number and term. It's represented by the letter I, so it's a little lowercase cursive I. So we'll be looking at what that means, how we can use it, and when that comes into play for us, okay? So let's go ahead and jump right in. So classify each of the numbers represented below according to the sets to which they belong. If a number fits into more than one set, list all that apply. So remember, we looked at these before: whole numbers, integers, rational, irrational, real, complex. Complex is our new name for not real. Complex is where we have our imaginary numbers at, is in the complex number system. So let's go ahead and begin. So we're looking at number 1 to start. Number 1 is pi. First of all, is pi a whole number? No, definitely not. Is pi an integer? No. What about rational? Nope. Is it irrational? Yes, pi is irrational because it is a never-ending decimal that goes on forever. Now, irrational is still part of the real number system, so it is still a real number. So it's still a real number. So if you say that a number is a whole number, an integer, a rational, or an irrational, that's all part of the real number system. If you say a number is a whole number, that means it's also an integer, rational, and real. So these numbers, they build upon themselves. So if it's a whole number is the smallest that we're going to look at. So everything else is bigger, and whole number is a subgroup of that. So whole number would have all of them in it. All right, so for number 6, we have 9/3. Now, 9/3 currently is wrote as a fraction, but what is 9/3? It's 3. So 3 is a whole number. It's also a integer then. It's also a rational number, and it's also a real number. So anytime you have a whole number, you're going to have the whole list of them. So that will happen no matter what, because every whole number is a subgroup of integers, which is a subgroup of rationals, which is a subgroup of real numbers. So they are all connected. Now, number 9, we have the square root of -40. Any other time, if we would see this, we'd say, oh, not possible. We can't take the square root of a negative number. Now we can. In the complex number system, you can take square roots of negative numbers. So this is part of the complex system. So this is completely possible now. So now, instead of being able to say not possible when you see a negative under the square root, now you can actually do something. So we can expand on that now. All right, next section, simplifying radicals and imaginary numbers. So simplify each radical expression below. So we have both whole numbers and radicals in the same expressions. Now, when we have problems like these, you can't combine the 3 and the root 2 together. They're two different things. So you can kind of think of them as whole numbers and variables when you're combining them. We can't combine them together. We can write 3 plus x if we had a variable, but we couldn't actually combine them at all. When we have, so like here we have the square root of 2 plus the 3 square root of 2. The roots aren't going to change when we're adding. The number out front will. So this is a 1 root 2 and this is a 3 root 2. They're being added together, so we'd end up with a 4 root 2. When you combine roots, the number under the square root has to be the exact same number. We can't combine different roots together and just add or subtract them. It has to be the same number. So like I said, you can kind of think of them like a variable. We can't add x and y together. We can't combine those, have a 1x plus a 1y and get a 2xy. That doesn't work. It has to be the same number under the root. So what we're looking at here is number 10. We have 3 plus root 2 minus 7 plus 3 root 2. So we're going to combine the real numbers. So we have 3 minus 7. 3 minus 7 is -4. Then we have, and remember, anytime, just like with variables, if you have just the root, it's a 1 root that value. So 1 root 2 plus 3 root 2. So 1 plus 3 is 4, so plus 4 root 2. This is our answer. We can't simplify this any further. We want to leave it just like this. We want to keep the radical in our equations, okay? All right, number 12. Now notice, we have 12 and 48. Now we can't just say that this is the square root of 60. It's not possible. We can't add them together like that. Instead, we have to figure out how to rewrite the square root of 12 and the square root of 48 so that it's some number root like 2 or 3, something like that underneath this root. So what is a perfect square that goes into 12? Well, 4 goes into 12, right? So we've got, I'm going to write it up, I'll write it, yeah. 4 times 3 gives us 12. Now, what's a perfect square that goes into 48? Now, you're probably thinking, well, 4 goes into 48, so we can take that out. But is that going to give us the same number under the square root? Because we'd have 4 times 12. No, it's not. So we need to figure out another perfect square that goes in there. Does 9 go in there? Nope. What about 16? Yes, 16 times 3 goes into 48. So square root of 4 is 2, so we end up with 2 root 3 plus square root of 16 is 4 root 3. Now our roots have the same value underneath, so we can add these together. So 2 plus 4 is 6, square root 3. Once again, the square root of 3 is going to stay the same. We can't change that, okay? So this is our answer. So that's what you guys are doing on this section. So some of them, the square roots are already so that the same numbers underneath, you just combine them together. If you have more than one square root in a problem, just combine the ones that are the same. So hint for 15, just combine the root 7s and then the root 3s, and then don't try to combine them together because you can't simplify either of those roots further, okay? All right, the next section says to simplify, express as a complex number using I if necessary. So, like I said, I is when we have a negative under the square root. Now, for 16, if we multiply the square root of negative 2 times the square root of negative 2, essentially what this is saying is we're taking the square root of negative 2 and we're squaring it. Now, what happens when we square a square root? They cancel each other out, right? So this is just negative 2. So anytime you multiply two square roots together and they have the same number underneath the square root, you're going to get an answer of just what was under the square root. So your answer for 16 is negative 2. Now for 17, we have 7 plus the square root of negative 25. Now, can we take the square root of negative 25? No. Can we take the square root of 5 or 25? Yes. Now, 7 plus the square root of 25 times negative 1. That gets us our negative 25 under there. Now, we can take the square root of 25. It's 5. So we have 7 plus 5 times the square root of negative 1. Now, I, that little I that they mentioned, I equals the square root of negative 1. So this says the square root of negative 1 right here. So our answer is 7 plus 5i. So anytime we have a negative under the square root, we can eliminate that negative by taking and bringing an I to the outside of the square root, because the square root of negative 1 is I. So that just gives us an answer of 5i for that, because 25, square root of it is 5, square root of negative 1 is I. So 7 plus 5i. Now, we can't combine the 7 and 5i. They're going to stay exactly as they are. We can't change that at all. But that's going to be our answer. Now, On 21, we have 2i times 5i squared. So first we're going to take care of the 5i squared. So we've got our 2i times 5 squared is 25. I squared is I squared. Now, I squared equals -1. Now, you may be saying, well, how do you get that? Look back at number 16. Any number under the square root multiplied to itself gives us the number underneath. If I is the square root of -1, we multiply the square root of -1 times the square root of -1. That's the square root of -1 squared. So it's just -1. So if we square I, we get -1. So this 25i squared becomes just -25. So we've got 2i times -25. Now, 2 times -25 is -50i. Now, we can't do anything with just a plain I. That's going to stay I, just like that. But when we have an I squared, we can simplify that. When we have an I to the third power, we can simplify that. I to the fourth power, we can simplify that. So you're just taking the square root of -1 to whatever that power is. So simplifying that down and seeing what you get, okay? All right. Next section. So for the next section, we want to solve each quadratic equation over the set of complex numbers. So the first one we have here that we're going to do is number 23. So number 23 here. I'm going to erase this a little bit so I have some space. So we have t squared plus 24 equals 0. What's the first thing we need to do to try and get t by itself? Well, subtract 24. So we end up with t squared equals -24. How do we get rid of the squared? We take the square root. So we end up with t equals plus or minus the square root of -24. Now, -24. How are we going to simplify this? Well, we know we're going to have an I because there's the negative under there. Now, is there a perfect square that goes into 24? Yes, 4. So we're going to have we're going to have plus or minus 2i root 6. So t equals plus or minus 2i plus 6. So we just bring the I. So just like with the number, we bring the I out to the front of the square root. We don't want to put it behind it. We want to have it out to the front, okay? All right. The next section is solving quadratics. Use the discriminant to determine the nature of the roots to the quadratic equation. Now, the discriminant is b squared minus 4ac. So it's the part underneath the square root in our quadratic equation. So it's only the part underneath the square root. So for 26, our b is -5, our a is 1, and our c is 7. So b squared, so -5 squared minus 4 times 1 times 7. -5 squared is 25 minus 4 times 1 is 4 times 7 is 28. 25 minus 28 equals -3. Now, we got a negative number. When we get a negative number, it's a complex imaginary number. So this is complex and imaginary for what the roots would be, which means it's not actually touching the x-axis ever. It's floating up above it or down below it, but it's never going to actually cross. Now, when we have a positive number, that means we have two real rational numbers. When we have a 0, so we actually get a 0, that means there's only one real rational solution because it's sitting on the x-axis. So there's only one root for that. All right, so for 27, if we do this one, B is negative 5 again, so we have negative 5 squared.